Yeah, I have loaded the 3PT1 plus P controller closed loop system with negative feedback. The parameters can be displayed with this parameter box. The P has a gain of 10, all others have gain 1 here, and the time constants are our given values 0.3, 0.2, 0.05. Okay. If we have checked this step response in chapter 3.9, and this step response was an oscillating signal with you see with decreasing amplitude, so this is stable. Then we have increased this to 20, and remember our calculation of the step response shows now an unstable situation, so with 10 stable, 20 unstable, and now we have found the stability limit where we can say, okay, if this is smaller than 1, it is unstable, we have to check it, and if this is larger than 1458, this is unstable. So I go just to the value 1458.583, yeah, and say OK. And if I now calculate this again, you see the following reaction. Looks also unstable. So this is a contradiction to that what we have calculated. But this has something to do with inaccuracy of this numerical program. We have 512 points on one scale, and between each point we make 5 calculations. We can increase the calculation accuracy by just increasing the numbers here to any value where you can see there is no change. Here you see OK, also unstable. Let me go to 500 points, so this gives 500 times 500 25,000 calculations. This takes some steps, so you see also increasing amplitude. Okay, let's check. Warte mal. Input, output block. This has nothing to do with output block 4. Warte mal. Yeah, you see here again increasing amplitude, also with 500 steps. Let's go to 5,000. It's the maximum number of steps. I make a recalculation, and we have now to wait some seconds. Pop. And here you see also increasing number, so I think my my number is wrong. What is that? 14583. What is this? Yeah, typing error. 1458. I have typed in 1548. Okay, of course, this is unstable, yeah? 1458. Wow. That is the correct number. Now I go back to calculation, go down to again 5 points, recalc. Here you see, okay, increasing. Now I show you what happens if I increase now the calculation. Here you see, okay, there is a small increase. Now I go to 500, and then in this case you see here really no increase within 4 periods. So this is the proof that we have now the stability border reached with constant oscillation. If the gain is a little bit higher, as we have done in the previous simulation, you see increasing amplitude. If the gain is smaller, decreasing amplitude. This is the point where the amplitude is constant. We can now go to the same situation for negative values. We have found that negative 0.5 should be stable situation. Yeah, you have to go to larger times. You see final value is constant, stable. If the gain is more negative than -1, say 2, this result should be unstable, you see exploding. And if the gain is -1, we are at the stability border. We should see a ramp function, that is a border case integrating effect. For a closed loop system, of course, not good, but stable. That is what I want to show you. What happens in a good closed loop system. In a good closed loop system, we should have less oscillation, no negative output values. So I think negative case gives stability, but strange reactions of my loop system. If I go to say 5, I get a calculation which shows oscillation, and then final value is 0.8. Note, I want to have a 1, I get an 0.8. This is nearly 20% control error, and oscillation is still there. If I want to have very small oscillation, I have to decrease again, say to factor of 2, and then we get we don't need so many points here. An oscillation which is nearly acceptable, that is 50% overshoot. Final value is less than 0.7, so there is a big control error, but of course stable operation. So we can do the job with a P controller if we accept this final control error. Next step I want to show you is the case 2 situation, including simulation. Now, new calculation, case 2. T1, T2 are positive, but T3, so 1 is negative. Now the coefficients are independent of the sign of the t's, so the coefficients are the same. Now look for the signs of the coefficients. Look here for T3. If one time constant is negative and the other values are positive, then we see at once C3 is negative. And the consequence is then all other C0, C1, C2 also must be negative, otherwise we have unstable systems. Can the C2 and C1 be negative? Let's start here with C1. Of course, this could be negative if the negative time constant is in the magnitude larger than the both positive time constant. Then C1 changes the sign. So what we can mathematically write down is, let's start with C1, finally to C0. C1 is the sum of the three time constants, must be negative, leads to the statement. I make the following thing. If T3 is negative, I write in the following form to have clear the view of the negative sign. T3 is replaced with negative T3 magnitude. Then I see the minus sign in my equations. So you see, I write now T1 plus T2 are positive, negative minus T3 magnitude must be smaller than 0, or in other writing, I now bring negative T3 on the right side. T3 must then be larger, the magnitude of T3 larger than the sum of the T2s. the other both time constants. In our case, in a numerical example, I make the following thing. I make the large time constant negative, and I leave the both other time constants with the same value, and I check if this is true. T1, T3, no, T3 is negative. I want to have, sorry, T3, the numbers. I make T3 now negative 0.3 and T1, T2 are positive. So this is 0.3 is larger than the sum of the both other is 0.25. So this is okay. But you see, my controller has no influence to this inequality. If the time constant doesn't fit to this system, then I can nothing do. Then the system becomes unstable. Furthermore, C2 must be positive, and C2 is a product of the mixed product of the three time constants. T1, T2, T2, T3, T1, T3. Now I expressed with a negative T3 value. I extract the T3 out of the both last elements, so I can write T1, T2, a negative T3 magnitude times T1 plus T2, and this is C2, and C2 must be smaller 0. Now I bring this on the right side and divide by this. This is positive. Then T3 magnitude, the absolute value of T3 must be larger than T1, T2 product divided by T1 plus T2, the sum of those time constants. In our case, T1, T2 product gives 0.2 times 0.05 divided by the sum is 0.25. This gives 0.04, and T3 magnitude is 0.3, and 0.3 is of course larger than 0.04, so this is in our case okay. Yeah, in this case okay, in this case okay. So finally we can say the system is stable if C0 is also negative. C0 was 1 plus k, must be negative, so we can say okay, for k we can solve this inequality very simply to say k must be smaller than -1, first condition. This is necessary but non-sufficient. To get this sufficient condition, we have to check the inequality for degrees for polynomial functions where n is 3. This is the inequality C1, T2 must be larger than C0, C3. Check C1, C2 must be larger than C0, C3. If we put these coefficients into our equation, then we get C1 is the sum of the t's, and C2 is the sum of the mixed product of the t's. And on the left side we have C0, that was our 1 plus k, and T3 was the product of the three time constants. Okay, we now want to have an equation, a border equation for k. So we have to divide now by the product t1, t2, t3. We know this product is negative. If we divide by this, we write unchanged sum of the t's. We divide again the t1, t2, t3 in each case for the single elements here and get 1 over t1 plus 1 over t2 plus 1 over t3. And this must be now we divide by a negative number, so this gives a swap of the inequality sign. So we have to write on both sides -1, and now this sign is changed to this value. So k must be larger than this, and this gives in our numbers with numbers gives a k must be larger than -1 plus the sum of the t's. Now with these values, sum of the t's is 0.25 minus 0.3 is negative 0.05. Negative 0.05 multiplied with the sum of the inverse of the t's is, okay, 1 over t1 was 20 plus 1 over t2 was 0.2, 1 over t2 is in 5, negative 1 over 0.3 is 3.3 period with a negative sign. So this gives a border value which gives a value of negative 2.083 period. So we get a result which is very astonishing. The result is the system is stable if and only if negative 2.083 period is smaller than k, and k is then smaller than -1. On the k-axis, we have here a 0, here a -1, and here a -2.083. Then we can say, okay, k must lay within this range. Here we have stability, and this is unstable, and this is unstable. So we have a very small range, but there is a range where we have an unstable open loop system, and we can control this with a P controller within this range, and then my Hurwitz criterion postulates stability that has to be proven with my simulator. We want to see this, yeah? Simulation, and this together ends up in video 46. Is that right? Das kann ja nicht sein, warte mal. Yeah, this must be 47. Sorry. 47. The numbers sometimes should be right. Okay, start simulation. Now, in this simulation, we exchange the time constant of the block number 2 with positive 0.3 to negative 0.3. So we know the open loop without control is unstable. We know for blocking K, system must be unstable. Proof. Explosion. Unstable. We know for negative 0.5, we are outside our stability range. System should be unstable. Proven. So for large negative values, so 2.5, we are unstable. We have a border of stability at negative 2083 2083. Say OK. Calculation, how many points to have good accuracy. You see stable oscillations. We are now at the border of stability, and there is a second border of stability, which is the gain -1. Say OK. We should see a ramp function. Yeah. So this is exactly that what we want to see. And finally, now we go within our range. We go just in the middle between the borders and check if this then is a good controller. So we go to -1.5. -1.5 is nearly in the middle of my range, stability range. There we should see step response, which is stable. You see, stability is proven, but note control error is large. We want to have a 1, and we get final value 3, and there are strong oscillations. And yeah, I think this is stable, but that is not sufficient for a good closed loop system. This will be discussed then in the next chapter 5, where we will go to other stability criterions. So in this chapter 4, I will close with the Nyquist criterion, a totally different method to check stability. We need the Bode plot of the system, but this is very helpful for chapter 5. So I think this comes with the next video. So the last point of chapter 4 and the chapter 5 just is discussed in the video number 47. Okay, stop here.